All right, today we're going to pull back the curtain on a concept that's pretty much the secret handshake of science and engineering, significant figures. You can think of it as a hidden language that tells us just how much we should trust a number. So, let's dive right in.
So let's just kick things off with a simple question. Is a trip of 100 miles the exact same thing as a trip of 100.0 miles? Now, your gut reaction is probably, yeah, of course. But you'll see that in the world of measurement, there's a lot more going on than you might think.
Believe it or not, the answer is a big, fat no. They are not the same thing at all. And I know that sounds weird, but figuring out why they're different is the whole point of this. It's the key to understanding precision, and it's the exact problem that significant figures were invented to solve.
So, how in the world do we show that difference? Well, we use a special kind of language, a set of rules that tells anybody who looks at our numbers exactly how precise we were when we measured. And that language, you guessed it, is called significant figures.
So here's the official definition. Significant figures, or sig figs as you'll hear, are basically all the digits in a measurement that we are absolutely sure about, plus one final digit that's a bit of an estimate. It's really just a way of being honest about how good our measurement tool actually is.
I love this analogy. Think of it like a camera lens. A measurement with only a few sig figs is like a blurry photo. You can kind of tell it's a person, but you can't see their face. But a measurement with more sig figs, that's like a super sharp, high-resolution photo where you can see every little detail. More sig figs just give you a much clearer picture of reality. Okay, so if we're going to speak this language, we've got to learn the grammar, right? So let's break down the toolkit, the simple rules we need to figure out exactly which digits matter in any given number.
The good news is, there are really only 4 core rules to get the hang of. The first 3, they're pretty easy, but that fourth one, the one that deals with zeros at the very end of a number, that one's got a little twist. Let's break them down one by one.
All right, rule 1 is the easy one. Any digit that isn't a zero is always significant, no exceptions. So in a number like 234, the 2, the 3, and the 4 all matter. That gives us 3 sig figs. Simple as that.
Rule 2 is all about what I like to call captive zeros. Zeros that are sandwiched between other digits. If a zero is stuck between 2 non-zero numbers, like in 101, it counts. It can't get away. So 101 has 3 significant figures.
Now what about zeros at the front, like in 0.0025? Well, you can basically just ignore them. They aren't telling you anything about how precise the measurement is. They're just placeholders, showing you how small the number is. So we only count the 2 and the 5. That's just 2 significant figures.
Okay, here it is, the trickiest rule. Zeros at the end of a number. It all comes down to one simple question. Is there a decimal point anywhere in the number? If there's no decimal, like in 2500, those zeros are just placeholders. We only have 2 sig figs. But the second you add a decimal, like in 2.50, that trailing zero suddenly becomes important. It means you measured that spot precisely, so 2.50 has 3 sig figs. That decimal point changes everything.
All right, let's do a quick pop quiz. Take a look at this number right here, 0.00450. Based on the rules we just went over, how many significant figures do you think it has?
Did you get it? The answer is 3. Let's walk through it. The leading zeros? Nope, they don't count. The 4 and the 5? For sure. And what about that 0 at the end? Well, because there's a decimal point in the number, it absolutely counts. So that's 3 sig figs. Awesome.
So let's just do a super fast recap. Non-zeros are in, zeros stuck in the middle are in, zeros at the very beginning are out, and trailing zeros at the end are in, but only if there's a decimal point. That's your cheat sheet right there. Okay, so knowing how to count sig figs is half the battle. But the real power comes when we actually start using these numbers. When we add, subtract, multiply, and divide them.
Now, this is really important because there are 2 totally different rules for doing math with them. When you're multiplying or dividing, you look at the total number of sig figs in your starting numbers. Your final answer can't have more sig figs than your least precise number. But for addition and subtraction, you forget all about that, and you only look at the number of decimal places.
Let's really hammer this home, okay? Which operations make you focus on the decimal places? That's right, addition and subtraction. For everything else, multiplying, dividing, you're just counting up the total sig figs.
So, let's bring this all together. We've learned the rules for counting them and for using them in calculations. But now let's see why this isn't just some random math exercise, but something that has real-world power.
And that brings us right back to the beginning.
back to that very first question I asked. Now that we've learned all this, let's look at it again. Is 100 miles the same as 100.0 miles?
Now we can actually answer this like a pro. The number 100.0, with its decimal point, clearly has 4 significant figures. We are sure about the 1, the first 0, the second 0, and even that first decimal place. But 100, without a decimal, according to our rules, those trailing zeros are ambiguous. They're just placeholders. So we can only really be certain about that first digit, the 1. That gives it just one significant figure. The difference in precision is absolutely massive.
For the real difference, when you boil it all down, is just one word: trust. You can trust the measurement of 100.0 miles with a ton of certainty. But 100? It's just a rough estimate. You can't rely on it in the same way.
And this isn't just an academic thing. In medicine, the difference between 1.0 milligram and 1.00 milligram of some powerful drug could literally be life or death. In engineering, you better believe the stability of a bridge depends on measurements with the right precision. And in science, nobody can replicate your experiment if you aren't honest with your numbers. Precision really matters.
So I'll leave you with this final thought. If your life was on the line, if a doctor was figuring out a dose for you, or an engineer was designing the plane you're about to get on, how many significant figures would you want them to use? This language isn't just about numbers, you see. It's about communicating a level of certainty that all of us can depend on.